Hello everyone. In this video we are going to be covering one of the very important concepts in the entire section, which is mole concept. And not just in terms of weightage in the competitive examinations, but also in terms of the importance and the interconnectivity of this idea to the other topics in physical chemistry. This is probably one of the very important areas. So to begin with, we'll just start our the mole concept learning with understanding of what is an atom. So we know atom is the building block of matter, and it defines the chemical nature of the element. Like say we have iron atoms means that represents one type of chemical nature, gold atoms means that represents another type of chemical nature, and so on. Now atoms will be combining with covalent bonds between them. Atoms of same element or atoms of different elements also, they will combine to form molecules. Like here we have H2 which is formed by the combination of hydrogen atoms, N2 formed by the combination of nitrogen atoms. This O3 is ozone, it is formed by the combination of the oxygen atoms. And we can also have examples of molecules like methane, CH4, it is formed by the combination of carbon and hydrogen atoms. We can have CO2, carbon dioxide, formed by the combination of carbon and oxygen. We can have ammonia, formed by the combination of nitrogen and hydrogen, and so on and so forth. Other than the molecules, we have one more manner in which the atoms can actually combine, and when they combine in this manner, they will be forming ionic compounds. So when atoms of, say for example, sodium, they lose electrons, they will be forming sodium plus ions. And if these electrons are taken by the chlorine atoms, thereby they will be forming Cl minus ions, chloride ions. The Na plus and Cl minus ions, they will get attracted by the electrostatic forces of attraction and form a solid structure. This is what we call as an ionic solid or ionic lattice. So when we look at the chemical substances around us, either we are going to be having the molecules or we will be having the compounds. Molecules will be having the covalent bonds between them, and compounds will be having the ionic bonds in them. This is the basic difference between the molecules or compounds. Now what exactly happens in a covalent bond, what exactly happens in an ionic bond, we will get to know when we go to the chemical bonding section. Now this is one of the very important aspects in the olden days, when what atom is, when the idea of atom itself is not very much clear to people started looking for what could be the mass of a single atom, and this is what they called as the atomic mass. Now when the atom itself is so tiny, it is possibly not a realistic approach to find a method to directly know what is the mass of the atom, because atom is going to be very small particle. So the approach that has been taken by people is to give a relative mass. So what exactly is this relative mass is, we define the mass of one atom, or basically we define a reference or a standard by using mass of one atom. So initially they took the standard by using the hydrogens, then they changed the standard to the oxygen, and finally today we are talking about the standard to be based on the carbon 12 atom. So carbon has got two isotopes, carbon 12 and carbon 14. So this current standard of relative mass is defined with respect to the carbon 12. So what is this relative mass unit? This is called as atomic mass unit, in short AMU. It is defined as 1/12 of the carbon 12 atom mass. So when we look at mass of the other atoms, we would not know how much is the exact value, but there are methods which people used back then itself to find, or rather to express, the mass of the other atoms using this relative mass method. So when we look at the mass of the hydrogen using the AMU is 1/12 of the mass of the carbon 12 atom. The atomic mass of hydrogen is coming around 1 AMU. It is not exactly 1, it will be 1.006 or 7, but we'll just look at the number part of it, whole number part of it. Carbon is 12, nitrogen is 14, oxygen nearly 16, fluorine 19, and sodium 23, chlorine 35.5. So please keep one thing in mind, these are the atomic masses and they need not be whole numbers. Iron nearly 56, not exactly 56, but it will be approximately 56. Copper 63.5, silver 108, potassium 39, sulfur 32, phosphorus, calcium 40, magnesium 24, aluminum 27, silicon 28, and lead 207. So these are some of the atomic mass values of common elements, and there are many more. So as we look at the respective elements in the problems, sometimes we'll be required to use the atomic masses. So all these are the atomic mass values which are expressed in terms of this relative unit called as AMU. Now when the AMU unit was defined, people didn't even know what is the exact value of the AMU. The value of the AMU is derived at a later point of time. So this is how the concept of atomic mass has started. Now when we look at some of these elements, they would exist in different isotopic forms. So isotopes are basically like in the case of hydrogen has got three isotopes, H11, H21 and H31. So isotopes are the atoms of the same element, which means they will have the same atomic number, but they would be having different mass number. This happens because their number of neutrons will be different. That is what is the case of an isotope. So when an element is having different isotopes, and obviously different isotopes will be having different masses. So for those elements we will talk about the average atomic mass. The average atomic mass is basically the weighted average. Like if you look at the average atomic mass formula, we'll just find it out by multiplying the abundance value of the respective isotope with the atomic mass of the isotope and add the summation of it whole divided by 100. This will give you the weighted average of the atomic mass. Now just to understand this by using an example, if say for example we have argon, which is having three isotopic forms, the atomic mass values of the respective isotopes are given here, and the corresponding abundance values in terms of percentage also given. If we want to find what is the average atomic mass of the argon, so we will be simply multiplying the isotopic atomic mass with the fractional abundance. Basically when you multiply percentage and divide everything by 100, you will be getting the fractional abundance. So when we multiply each of the atomic masses with the fractional abundance, and the total value is what is going to be the average atomic mass. So in this problem you can see each of the isotopes, they have got their own atomic masses, but whenever we talk about the atomic mass of argon, we'll take the value to be 39.352. Same is the case with chlorine also. So when we discussed about the chlorine, right, we saw that the atomic mass of chlorine is given as what, 35.5 AMU. This is because chlorine itself exists in two isotopic forms, chlorine 35 and chlorine 37. So the atomic mass that we are discussing for chlorine is actually the average atomic mass of both the isotopes. Same is the case with hydrogen and so on. Like whatever the elements which are having significant existence of the isotopic forms, we will consider the average atomic mass of the isotopes. Now when we look at mass of an atom, we were only able to express this as a relative measurement. Like we have taken AMU as a relative mass standard, and we were able to get the mass of all the other atoms by using that relative standard. But some scientists they have coined the idea that what will be the number of particles. This is exactly what apparently has happened when Avogadro tried to look at the most important number in chemistry, which is the Avogadro number. What he did was, like say for example the atomic mass of carbon is 12 AMU. So he took 12 grams of carbon and tried to find what is the number of carbon atoms in that. The count he got was 6.022 into 10 power 23. And he again took say for example 4 grams of helium. First is 12 grams of carbon, second is 4 grams of helium. In that he found that there are 6.022 into 10 power 23 atoms of helium. So whenever the atomic mass value expressed in grams is taken, the number of atoms in the particular mass is always coming out to be a fixed number, and this is what later called as the Avogadro number, whose value is equal to 6.022 into 10 power 23. So this mass which is nothing but the atomic mass value expressed in units, is actually called as what? Gram atomic mass. And gram atomic mass of any substance contain Avogadro number of atoms. Gram atomic mass of any substance contains Avogadro number of atoms. Like say for example, as we're discussing, whenever we take the gram atomic weight, it will be containing 1 mole of atoms. This Avogadro number is also called as mole. So like the way we say, if I say dozen means what? 12. Okay, so if I say century means what? 100. In the same manner, whenever we talk about mole represents Avogadro number of particles. And like we discussed in the case of carbon, the atomic weight or atomic mass. So generally in physics, when we talk about weight is supposed to be the gravitational force acting on the object. So weight will be equal to m into g. But in the context of chemistry, we will be using weight and mass to refer to the same thing. So if I say atomic mass or if I say atomic weight, they both are actually referring to the same thing. So the atomic weight of carbon is 12 AMU, as we know. The gram atomic weight of carbon will be 12 grams. And this will be containing 6.022 into 10 power 23 atoms of carbon, and that is what we will be calling as 1 gram atom of carbon. So this is the concept of the gram atomic mass. Now once the idea of gram atomic mass is discovered, people were able to use this idea to find what is the exact value of the atomic mass unit. So the definition of atomic mass unit is 1 AMU will be equal to 1/12 of an carbon 12 atom mass. This is the definition of the AMU. So 1/12. We know that when we are taking 1 mole of carbon 12 atoms, the mass is 12 grams. So if I want to look at what is the mass of one atom, that will be 12 grams by the Avogadro number, because Avogadro number of atoms are measuring 12 grams. So one atom will be measuring 12 gram by Avogadro number. So if we cancel the 12 and 12 here, the value will be equal to 1 gram by Avogadro number. This is what is AMU, and if we try to look at it, the value will be 1.67 approximately into 10 power minus 24 grams, or 1.67 into 10 power minus 27 kg. So this is what is the AMU. So one atomic mass unit, you can see how small the value it is. It will be equal to 1.67 into 10 power approximately 10 power minus 27 kilograms. This is the value of the atomic mass unit. Now whenever we look at covalent substance, we talk about the molecular formula. So if say for example we talk about ammonia, so we'll say ammonia can be represented by a formula NH3. So what exactly this NH3, this formula communicates to us is, it tells us that in one molecule of ammonia, if you take, there is 1 nitrogen atom and then 3 hydrogen atoms. If I say that the molecular formula for glucose, it's a very important organic compound, is C6H12O6, then it will communicate to us that in every one molecule there are 6 carbons, 12 hydrogens, and there are 6 oxygens. This is what we will be calling as the molecular formula. There is one more formula that we can talk about for the substances which will exist in the covalent form, that is empirical formula. So what this empirical formula represents is, sometimes we may not be interested to know exactly what is the count of carbons, what is the count of hydrogens, and what is the count of oxygens. We may be interested to know which element is present in a higher proportion or dominant proportion in terms of the count. So if you can give a simple ratio of the elements present in the molecule, that is what we will be calling as the empirical formula. What it is, we'll just look at by taking the example. Say we'll go back to the same thing, glucose. So the molecular formula for glucose is C6H12O6. Here if you look at what is the ratio in which these atoms are present, it is 6:12:6. If you go for the simple ratio, the simple ratio will become 1:2:1. So if we can give a formula based on the simple ratio, which happens to be CH2O, this is what we will call as the empirical formula of glucose. Now this will tell us, if you take glucose as a substance, then hydrogen atoms are present in the higher proportion. That is what the empirical formula will be able to communicate to us. So we have a conversion also between the two formulas. As you can see here, the common factor which we are cancelling here is 6. So the relation will be molecular formula will be equal to empirical formula, where we multiply the empirical formula atoms count by the conversion factor. Like we take the same example of glucose. So here the conversion factor is 6. So if you multiply each of the atoms count by 6, then the formula becomes what? C6H12O6. That becomes the molecular formula. So this is the conversion between the molecular formula and empirical formula. Molecular formula gives the exact count of atoms. It completely describes what is the molecule composition. Empirical formula, it gives a simple ratio. It will be providing an idea of what are the atoms which are present in dominant proportion in terms of count, and what are the ones that are present in lesser proportion. Now for the covalent substances, the way we had molecular formula and empirical formula, when it comes to the ionic substances, we have something called as a compound formula. So compound formula is more similar to the empirical formula, where here in a ionic substance we will not be having molecules. We have oppositely charged ions which are arranged in the form of a lattice or an solid structure. Now when we look at an ionic substance, what we will be having is ions. If we take a ratio of the ions present in that ionic substance or complex, we call it as the compound formula. So for example, if I look at the NaCl substance, what happens in NaCl is, if you really count the number of sodium atoms and number of chlorine atoms, or number of Na plus ions and number of Cl minus ions, the ratio of the two is going to be 1:1. So the compound formula will be NaCl. Whereas if we go to magnesium chloride, you will find that the ratio of the two atoms will be 1:2. That is why the formula becomes MgCl2. Now for a compound, right, when we are expressing formula, sometimes we also indicate the water molecules present in this ionic compound or the complex. Like say for example, when we talk about the copper sulfate will be having 5 water molecules. Every copper sulfate entity will be having 5 water molecules. This water is what we call as water of crystallization. So when the ionic crystal is getting formed, some water molecules also will be getting embedded into the crystal. They will be going and occupying the empty spaces that are there, and this water will give rise to certain properties for these substances. But the thing is, when we are giving the compound formula, when there is this water of crystallization, we must express that also. I mean, all that we'll do is we'll put a dot after the compound formula. We'll put a dot and then write the number of water molecules. So this is what is the compound formula. Now the way we talked about mass of an atom, we can also talk about what is the mass of a molecule, and that is exactly what we call as molecular mass. So molecular mass is nothing but mass of the atoms, all the atoms present in a molecule. Like say for example, if we talk about ammonia, there is 1 nitrogen atom and then 3 hydrogen atoms. So which means the mass of the nitrogen is 14 AMU, and 3 hydrogens means 3 into 1, it will be 17 AMU. That is a molecular mass of ammonia. Same way, if you want to find the molecular mass of say for example urea. Urea is another important chemical substance, NH2CO, NH2, that is the formula for urea. So we will be having 2 nitrogens means what? 2 into 14 plus totally there are 4 hydrogens, 4 into 1, and then there is a carbon 12 plus there is an oxygen 16. So total will be 60 AMU. So we can find the molecular mass of any molecule. Like say for example, we have glucose itself. Glucose is C6H12O6. So there are 6 carbons, 6 into 12 plus 12 hydrogens, 12 into 1, and 6 oxygen, 16 to 16. So totally if you add all the numbers, it will be 180 AMU. So this is the way in which we will find the molecular mass of the corresponding covalent substance. Now apart from the molecular mass, since for a covalent substance we also talked about the empirical formula, we can also define something called as an empirical mass. So empirical mass is nothing but the mass that you derive just from the empirical formula. Like when we go back to the glucose example, we saw that the glucose empirical formula will be CH2O. So the mass that we get from the empirical formula will be 12, 1 carbon, 2 hydrogens, 2 into 1 plus 1 oxygen, 16. So if you add up the numbers, it will be 30 AMU. So we see one interesting relation between the two, the empirical mass and the molecular mass. The molecular mass will be, for the glucose C6H12O6, it will be 180 AMU. So the relation is molecular weight, which is 180 AMU, will be equal to empirical or the formula weight, which is 30 AMU, into the conversion factor 6. So we had a similar relation, because molecular formula will be empirical formula and multiply the number of atoms by the conversion factor n. So this is what is the molecular formula and then empirical formula. Now, just like the way we have talked about what is the mass of 1 mole of atoms, we can also measure what is the mass or weight of 1 mole of molecules, and that is what we will be calling as the gram molecular mass. Like say for example, if we look at ammonia, mass of 1 molecule of ammonia will be 17 AMU. If you take mass of 1 mole or 6.022 into 10 power 23 molecules of ammonia, that mass is what we are calling as the gram molecular mass or molar mass, and the value will be simply equal to molecular mass, but it will be expressed in grams. That is what is the gram molecular mass or molar mass. Now the relation is just similar to what we had in the case of the atomic mass and then gram atomic mass. So if we have the gram molecular mass or molar mass of a substance, that contains Avogadro number of molecules. Now similar to what we are using for the covalent substance, we also have a gram formula mass. Basically, if you take an ionic compound and we look at 1 mole of these chemical entities that make up this ionic compound, that mass will be called as what? The gram formula mass. Like in the case of MgCl2, if you take up 1 mole of the chemical entities, means we will be having 24 grams of magnesium and 2 into 35.5 grams of chlorine. So it will be 24 grams plus 2 into 35.5 will be 71 grams. Totally it will be 95 grams. Same way, if you take calcium carbonate, this is another ionic substance, we'll have 40 grams plus 12 grams plus 3 into 16 grams. Totally it will be 100 grams. So this is what we call as the gram formula mass. So for the atoms we have gram atomic mass, for the molecules we have gram molecular mass, and for the ionic substances we are having the gram formula mass. So these are in terms of the atomic mass, molecular mass, formula mass, and gram atomic mass, gram molecular mass, and gram formula mass of the chemical substances. Now just to summarize everything into one area, this is what is the most important piece, the conversions part of it, because while solving problems we may be required to convert the amount given in mass into the count, or the count into mass, or sometimes the count into volume or mass into volume, especially when you're talking about the gases. So we'll just look at what it is. Now whenever we take 1 gram atom of an element, that is what we are calling as what? 1 mole. This will be containing Avogadro number of atoms. So Avogadro number, the exact value is 6.022 into 10 power 23. If you take 1 gram mole of a substance, that is what is our the molecular mass. This contains 1 mole of molecules, means what? It contains 6.022 into 10 power 23 molecules. If you take 1 gram formula mass of the substance, this is for the ionic substances, this will be containing 1 mole of the chemical entities, which means what? 6.022 into 10 power 23 chemical entities. Now if the substance happens to be a gas, then 1 mole of any gas at the STP conditions occupies 22.4 liters. That is the conversion in terms of the volume. So based upon these conversions, we can try to have some formulae which will be using quite often. Like say for example, if you want to find the number of moles for the molecular substances, the number of moles will be the given mass, whatever the given mass in grams, divided by the molar mass. So when we divide the given mass by molar mass, we are going to be getting the number of moles that are present in the particular substance when we're talking about the molecular substances. Like say for example, if we take the case of ammonia, the molar mass is 17 grams. Means if somebody gives me just 17 grams, then the given mass is 17 grams divided by the molar mass is 17 grams, the number of moles will be equal to 1. If somebody gives me 34 grams, then given mass is 34 grams, molar mass is 17 grams, the number of moles will be equal to 2. When it comes to the atoms, if you want to find the number of moles of atoms, then it will be the given weight in grams by the atomic weight in grams, or the gram atomic weight. Like say for example, if somebody gives me 56 grams of iron, I want to find what is the number of moles of iron atoms in this. So given mass is 56 grams, divided by the gram atomic mass will be 56 grams. So that has got exactly 1 mole of iron atoms. Then since we are saying 1 mole of any gas at the standard temperature pressure conditions occupies 22.4 liters, we can also find the number of moles of the gas by using the volume conversion. So if somebody gives me 22.4 liters, then the number of moles in that will be the given volume 22.4 liters divided by the molar volume will be 22.4 liters. It will be equal to 1 mole. If somebody gives me 44.8 liters of a gas, then the number of moles in this sample given to me will be, given volume is 44.8 liters divided by the 22.4 liters, the number of moles in the sample will be equal to 2. Now the other important thing is in terms of the count of particles. So in all these formulae, basically we are trying to find the number of moles. So we were first trying to find the number of moles of molecules based on the mass. Then we have looked at how to find the number of moles of atoms based on the mass. Then we have looked at how do you find the number of moles of gases using the volume conversion. Then we are going to look at how do you find the number of moles of particles by using the count. So we know that every 1 mole will be Avogadro number of particles. So the number of moles will be given by the actual count of particles given to us divided by the Avogadro number. So if somebody is giving me 6.022 into 10 power 23 particles, so the number of moles in this case will be what? The given number of particles by Avogadro number. Here it is equal to what? 1. If somebody gives me 12.044 into 10 power 23 particles, then the number of moles in this case will be what? The given number of particles by Avogadro number. Here it will be equal to 2 moles. So we can find the number of moles of particles by using this formula also, the given number of particles by Avogadro number. So these formulas will be able to help us in terms of doing these conversions, especially in the mole concept based problems. Now in all this, we have been using the idea of what is the molecular formula and what is the empirical formula. But how people would be able to find out what is the molecular formula and what is the empirical formula of a substance? Because to know what are the atoms present in the substance, we have qualitative methods which we will be discussing in the estimation and qualitative studies of chemical compounds. But to know exactly in what count they are present, which is given either by the empirical formula in terms of simple ratio or the molecular formula which gives us the exact count of atoms, we must be able to know what is the empirical formula or what is the molecular formula. So we are going to see how empirical formula and molecular formula can be derived based upon the weight percentage data of the elements. So whenever a compound is given to us and we have the information of weight percentage of the elements present in the particular substance, then from that information we will be able to find out empirical formula, and from empirical formula we will be able to find out the molecular formula. So we will see how we will go about finding it by using some examples. Let us say a compound is given to us where it is said that carbon is 71.23%, hydrogen is 12.95% and oxygen is 15.81%. The task is we need to find what is the empirical formula of the compound. So here we will be following certain standard steps in terms of finally arriving at the empirical formula. Let us just go one by one. Here whenever they give us the mass percentage of the elements, we will be writing down what are the atomic masses of the elements. Here carbon is given, hydrogen is given, oxygen is given. So carbon atomic mass will be 12, hydrogen nearly 1 and oxygen 16. Now the weight percentage in the given substance is carbon 71.93, hydrogen 12.95, oxygen 15.81. So weight percentage will basically tell us that if you take 100 grams of the particular compound, then 71.93 grams will be the carbon, 12.95 grams will be the hydrogen, and 15.81 grams will be the oxygen part of it. So from this data we can find what is the relative number of atoms. So whenever we divide, previously itself we were able to find, if you divide the given mass by atomic mass, we are going to be getting the count of atoms. If we divide the given mass by atomic mass, we are going to be getting the count of the atoms. If you divide given mass in grams by the atomic mass in grams, or the gram atomic mass, we are going to be getting the number of moles of the atoms. So here we are going to find what is the relative number of atoms present. We will be dividing what is the weight of the substance or the element in the compound by the respective atomic mass. So 71.93 by 12, it will give us 5.936, and 12.95 by 1, which will give us 12.95, and in the case of oxygen 15.81 by 16, which is equal to 0.988. This is the relative number of atoms present in the particular substance. Now when we want to go for the empirical formula, we need to know what is the simple whole number ratio in which these atoms are present. So to get the simple atomic ratio, what we do is we will take whichever is the least of the relative numbers and divide each of the other values by that. So this is one of the methods that is used to get the simple ratio of the atoms. So in this case, what is the least value? 0.988. If we divide 5.936 by 0.988, the value will be approximately 6. And mind you, here we may not get exactly perfect whole numbers sometimes. Even if I am getting 6.02 or 6.01, we can round it off to 6. Why? Because keep in mind that we are dealing with the experimental data, which can always have some errors. And in the case of the hydrogen, if we divide the relative number of hydrogen atoms with the number of oxygen atoms, 12.95 by 0.988, which will be 13. And in the case of oxygen, if I dividing 0.988 by 0.988, it will be giving us 1. So this is giving us what is the simple ratio of the atoms present. So carbon 6, hydrogen 13, and oxygen 1, and thereby the empirical formula becomes what? C6H13O. We'll try to understand this by looking at one more example. So a compound is given which contains carbon, hydrogen, and nitrogen, and these elements are actually present in a mass ratio of 9:1:3.5, and also they gave us the molecular mass. Molecular mass is given as 108, and we have to find molecular formula. As we discussed before itself, we can only find the molecular formula after finding the empirical formula. So let's just look at the steps involved. So here the elements given to us are carbon, hydrogen, nitrogen. Atomic mass of carbon 12, hydrogen 1, and nitrogen 14. The mass ratio given to us is carbon is 9, hydrogen 1, and nitrogen 3.5, which means for every 9 grams of carbon we'll have 1 gram of hydrogen and 3.5 grams of hydrogen. So we'll find the relative number of atoms in this. Relative number of atoms means we have to divide the mass of the particular substance by the atomic mass. 9 by 12 will be 0.75, here 1 by 1 will be 1, and here 3.5 by 14 will be 0.25. This is the relative number of atoms. To get the simple ratio of these atoms, we have to take the least among them and divide everything by that. So least among them is 0.25. So divide here, 0.75 by 0.25 will be 3, 1 by 0.25 will be 4, and the last 0.25 by 0.25 will be 1. So the empirical formula, which is based on the simple whole number ratio of the atoms, will be C3H4n. Now the problem is not yet over, because they are also asking us to find the molecular formula. For this they gave us the molecular mass. And how do we find out the molecular formula? For the empirical formula and molecular formula, there is a relation, and the relation is based upon the conversion factor. And remember, the same conversion factor also comes in the relation between the empirical mass and molecular mass. Since already we have the empirical formula, we can find the empirical mass. and molecular mass is given to us. So we can use these two to find the conversion factor. And once we have the conversion factor, since already there is an empirical formula, we will be able to find out the molecular formula. So let us look at the steps. So here the empirical formula is there already with us. We can find what is the empirical mass. Empirical mass is coming as 54, and the conversion factor will be molecular mass by empirical mass. Molecular mass already they gave as 108, divided by the empirical mass will be 54. So the conversion factor here is what? 2. So if the conversion factor is 2, we have to multiply each of the atoms present in the empirical formula by 2. So thereby the molecular formula of the compound becomes what? C6H8N2. So this is what is the approach. Now we have been talking about the atomic mass and molecular mass extensively, but how would people really find out what is the atomic mass and what is the molecular mass? Are there any methods to really find out? So there are couple of methods to find out the atomic mass and molecular mass of different substances, and the methods, of course, they'll have their own limitations in terms of what cases or situations they can be used, etc. So here we'll take a look at two methods that we'll use for finding the atomic mass. One is Dulong-Petit's law and second is the Cannizzaro method. And for the finding of molecular mass, we look at the vapor density method. So there is one more method called as colligative properties method. This we will be seeing in the solutions chapter, because when you talk about the solutions, there we will discuss about the colligative properties in detail, and also we will talk about how the colligative properties will be useful in finding the molecular mass of the substances. So we'll just take a look at the Dulong-Petit's law to find the atomic mass. It's a very basic law or simple law which says if you have a pure element and the atomic mass of the particular element multiplied by the specific heat value. The specific heat value must be taken in what? Calorie per gram. The product of the two will be 6.4. So for any substance in the pure form, the elemental form, atomic mass value into the specific heat in calorie per gram will be equal to 6.4. So this is what in simple the Dulong-Petit's law, and this law is generally used for the metals. And for the lighter elements like boron, carbon, silicon, this law will not be able to give you the exact atomic mass values. So this is a law which has a limited purview in terms of its applicability for the metals. Then the another law which was also very useful in the preliminary days of the entire atomic mass concept evolution is this Cannizzaro method. So Cannizzaro method is based on a simple idea that whenever we take the compounds formed by a particular element, we see the minimum possible mass in terms of every element, and among all the minimum possible mass values, whichever is the least, that will be the atomic mass of the substance. So we'll just take a look at what this actually means. Say for example, we are trying to analyze the compounds formed by the nitrogen. So we have so many compounds. Okay, so we have ammonia, we have nitrous oxide, we have nitric oxide, we have nitrogen peroxide, nitrogen trioxide, so many of them, and we will be having the molecular formula of the compounds. The nitrogen mass in this is 14, in this is 28, in this is 14, in this is 14, in this is 28. Now when we look at the nitrogen masses, the least of the nitrogen masses in all the compounds is keep on happening to be the 14, and that is what we will be concluding as the atomic mass of the nitrogen. This is the Cannizzaro method. Then coming to the approach to find the molecular mass, here we are going to be only looking at the vapor density method. So in the olden days, when the idea of molecular mass and molecular formula were not quite popular, there used to be a concept of taking the relative densities. So people used to compare the density of one substance with respect to density of the other substance, of course under identical conditions. And one such property is what we call as the vapor density. So generally whenever people say vapor density, they would take the density of the particular vapor to the density of the hydrogen under identical conditions. And it happens to be that the density ratio will be equal to the molecular mass ratio, which means if you take the molecular mass of the substance, the molecular mass of any substance divided by the molecular mass of hydrogen gas will be 2. This is what we have been measuring as the vapor density. So the relation is molecular mass of any substance divided by 2 will be the vapor density, and if you want to find the molecular mass, means molecular mass will be equal to vapor density into 2. So this is the approach to find the molecular mass of a substance from the vapor density. So for example, if I say that an unknown gas, the vapor density is 22 grams, then the molecular mass will be 2 times of that, which will be equal to 44 grams. And we know, just CO2 could be this gas. We are not saying CO2 is the gas, we are just saying CO2 could be this gas. Why? Because CO2 molecular mass is 44 grams. At the same time, there can be so many other gases also which may have the same molecular mass. So this is about the methods to find out the atomic mass and molecular mass.